And then if these three criteria are satisfied, we are happy. We say that the result is converged to, and then the next level is, it's called discretization or solution error, sometimes called mesh error. Learning best practices, how to really use a software and what's important. That's a little underrepresented. I think partly because professors don't use the software that much anymore, or if they have no time to teach the students. It's fun to do CFD, especially if everything works. And if
if it
you
doesn't
get
work?
consistent results. If it doesn't work, then you have to work harder. It's you have to work as long until you get satisfactory results. And I think that's sometimes a challenge, but in the end, it's fun. Like with everything in sports, in CFD, if you master something, at the end, it's fun.
Okay, let's do it, Georg. It's really an honor to have you on the show today. Welcome.
Thank you.
Today we'll
Welcome
talk about.
also.
Thank you so much. Yeah, today we'll talk about computational fluid dynamics, and you're kind of I would say, a big expert in the field. I think we've met 5 years ago in Dresden at the turbulence course at the university. This is where I first met you. So I really enjoyed the lecture, and now today we meet in this podcast. Maybe give the audience a bit of an overview. Like, who is Georg? What are you doing with ISimQ? And what does your day-to-day business look like?
Okay. Uh, should I think I start a little earlier. I studied mechanical engineering in Munich, and then I started to work as a student with my supervisor on computational fluid dynamics. I did my diploma work at MTU Air Engines, a jet manufacturer company in Munich. And then I joined Wolfgang Rodi's group in Karlsruhe to do a PhD on turbulence modeling. And after this, I spent 6 years at the University of Erlangen leading a computational fluid dynamics research group, where I also met Milovan Peric, whom you have interviewed a few weeks ago. And we sat in the same room for about 5.5 years. And then after the University of Erlangen, I got in contact with Georg Scheuerer from the University of Waterloo in Canada and his PhD students, who were just about to start a company called Advanced Scientific Computing. And George asked me if I would like to start the business in Germany. And then in 1990, we started the Advanced Scientific Computing in Germany, and with the code TaskFlow, which soon sold well, especially into the turbomachinery industry. And then after 7 years, Advanced Scientific Computing was purchased by AA Technology, a British company. I think it was a government organization, but then under Margaret Thatcher, everything got privatized. And so AA Technology became a stock market company. And then again, 7 years later, the AA Technology company was purchased by ANSYS, and then I was managing director at ANSYS and also responsible for support in Europe and for large customers. And then the being a manager was less and less fun. So 7 years ago, I and Thorsten Hansen, one of the support managers of ANSYS Germany, who worked in support for 20 years, and Paul Galpin, the main programmer of CFX or development manager of CFX, we started ISimQ, which stands for Innovative Simulations with Quality. And now we're doing CFD consulting, a little bit development, best practice development. We also engage in courses and short courses, like the Dresden short course is most likely happening again in September this year. And so many of our customers in the turbo industry, but actually general, but the large bulk comes from turbo machinery.
Is there a particular reason why you focus on turbo machinery? Is it just a personal preference, or do you see a big
I
big
think
gap in the market?
this is an inheritance from early TaskFlow times, because TaskFlow was, I think, one of the first codes who worked well for turbo machinery. And then, of course, we inherited some customers when we left ANSYS in this field. But in general, we do everything. In our first office location, we were neighbors with the Fraunhofer Institute in Germany for building physics. So we did also some building physics flows, and we also had short courses together with them. But I think it's simply that the demand to us comes mostly from the turbomachinery industry.
I see. ISimQ stands for, as you said, innovative simulation with quality, and we'll talk about some of the quality parameters and some of the best practices later on in the podcast. Maybe you could talk a little bit about the evolution of simulation in product design. So how have you seen it over the recent years, how it changed and how CFD has become more prevalent for an engineer, so to speak, in that tool stack?
Yeah, I think you could summarize this in two sentences. I think in the 20 years ago, it was product before simulation. Like first you build something, you design something and you build something, and then if it didn't work, you started to do some simulations and find out what could have gone wrong. And now I think it's simulation before product. It has changed. You do a lot of simulation, especially in our main application field, turbomachinery. I think both in hydraulic machines and in jet engines and gas turbines, I think the simulation software runs 7 times 24. And so I think simulation results have a bigger and bigger influence on the final product, on the final shape of the products. And I think it has become much, much more important. And that's why also simulation results have to have a better quality, because if the results are poor, the product will also be poor. So I think there should be a higher requirement, or there should be higher quality and accuracy requirements, because the path from simulation to the hardware has become shorter. And I think you can also see it from, if you look over the last 20 years to the software vendors, I think they all claim 10-15% growth over the years. True or not, but I think from knowing from my previous occupation, it's not far from the truth. So I think if you're over 20 years, you probably have 15 times as many software, or the revenue has increased by a factor 15 or so, and which also means companies don't spend money for nothing over a long time. And that's, I think, is also an indicator that the use of simulation has really grown in product development.
Would you say at the current stage it's a bit stagnant, or it's still growing? So people still require like high quality simulation? Because as we'll talk about later about this in the podcast, Georg, is we talk a lot about machine learning, AI, these kind of methods, which is as kind of an augmentation for engineers. So do you see kind of a stagnant behavior right now when it comes to front loading?
No. I think there is. I think even the large companies, the use of simulation is not saturated yet. And then I think if they have used smaller models in the past, they go to larger models and multiphysics simulations and also more advanced models. And then I think the simulation use pervades down to smaller and medium companies. So I think there's growth on both ends still. And that's also, I think, supported with the revenue numbers of the software vendors.
Yeah, definitely. Maybe it would be interesting for the listeners of this podcast, whether they are students, maybe starting their CFD journey, or maybe professionals. Where do you see the biggest problems when people maybe use CFD on a day-to-day basis? Where are the biggest problems? Like, does it come down to meshing, turbulence models? Where do you see the biggest mistakes made in the industry, or maybe from students?
I think the biggest mistakes are still made in meshing, but then I think there's also a big mistake, because at least in Germany I do not see too many courses for practical CFD or practical simulation. It's either very theoretical, or students are just thrown at the software and they use it. But I think this this learning best practices, how to really use a software and what's important, that's a little underrepresented. I think partly because professors don't use the software that much anymore, or if they have no time to teach the students. So I think the rate of inheritance of good practice from one generation to the next is not so high. So, but if you ask for one aspect, then I think meshing is still the biggest problem.
I think, Georg, I also seen on your website that you also do these kind of workshops. For example, when it comes to hexahedral meshing, so you actually have a separate workshop only on meshing. So you teach people how to actually mesh geometries, which I think is super interesting.
This is by my colleague and Thorsten when he was support engineer. When he educated young engineers, support engineers, he sometimes said, if a customer calls, you don't have to look at the results, just look at the mesh, because that already explained 3/4 of the problems. And so I think a good mesh lets a turbulence model shine or lets a numerical code shine. So I think if you do high quality in meshing, then the rest almost comes for free.
Yeah, I like that. That's good. Maybe could you maybe for the audience break down the errors, the nature of errors in CFD simulation, like what types of errors exist in the first place in CFD?
Yeah, okay. I think if you talk about numerical errors, we have this hierarchy. First we say, okay, the on the top is round-off errors, which means you need sufficient machine accuracy. That's mainly a problem if you have very stiff equation systems or very large variations in size or in the dependent variables like pressure. But this can always be cured by doing a double precision simulation or comparing single and double precision. If the results are the same, then you can live with single precision, which is usually cheaper, 50% or so, and requires less memory. And then because uh, all CFD codes use iteration, because the basic equations are nonlinear and they get linearized and then iterated, you need to control the iteration error, which means you have to converge to set the convergence criterion in a way that your target values like an efficiency or a maximum temperature changes only below a certain criterion if you would keep on iterating and in ISimQ we always look at three things. We look at the residuals of the equations, either an RMS norm or a maximum norm, checking that the largest residual meets the criterion. And then second, we use this coefficient of variation of our target quantities. Like we look at the floating standard deviation of a target quantity over, say, 25 iterations divided by its mean value. So if you have a steady state problem, then this coefficient of variation has to go to zero because standard variation of a constant is zero. And this is directly proportional to the iteration error. You can say if this changes, then less than 10 to the minus 5. If you would iterate more, then your change would be less than 10 to the minus 5. And the third thing, we always check the global balances of global mass conservation, global momentum conservation between inlet, outlet, walls, etc. It's for energy, it's basically the first law of thermodynamics for the domain. And then if these three criteria are satisfied, we are happy, we say that the result is converged to, and then the next level is, it's called discretization or solution error, sometimes called mesh error, because if you have a certain number of grid points and then you increase the number of grid points, then your solution will change. And the question is by how much will it change? And okay, this then you can quantify this discretization error. The best method is by so-called Richardson extrapolation, but for this you need solutions on 2 or 3 meshes.
Yeah.
That's why we always generate meshes that are scalable. If you have a mesh with 100,000, then we typically refine in all space direction by factor of 1.6, because 1.6 cubed is around 4. So if you refine by 1.6 in all space direction, you go from 100,000 nodes to 400,000 and then to 1.6 million and so on, because you need to change by a certain amount. Otherwise, if you only change little, the solution doesn't change little. And then it would be a wrong conclusion to say we are mesh independent. So it should be at least a factor of 4 or 8, like halving the mesh distance in all 3 directions. And then you can estimate the solution error, which is the difference of the solution on the grid you have minus the solution on an infinitely fine grid. That's the definition. But because you don't have an infinitely fine grid, you can use this Richardson extrapolation to get an estimate for the solution on the infinitely fine grid. And then you get a pretty good idea. okay, how accurate your solution is numerically. And if your boss wants 1% and you are at 5%, you have to tell him that you need to repeat the calculation on a finer mesh. And good code or a consistent code should also, whenever you halve the distance, the mesh width and its first order, then the error should halve. If it's a second order method, then the error should be mesh distance over 4. And so you should basically be able, if you do 2-3 simulations, to have a nice line extrapolating to infinitely fine mesh. And then from this you can directly tell your manager that if you want 1% accuracy, I need 3 million nodes. Or you just tell him, with the mesh I have this numerical accuracy, is it enough or not? And once you have controlled the iteration error, discretization error, then what's left are model errors or systematic errors. Model errors mainly from the turbulence model or multiphase flow model or combustion model, or the combination of those, I think, which you only can quantify by comparing to good data. And then there are also, of course, systematic errors, that something is in the experiment which is not in the simulations, and that's very often you only find out when talking to the experimentalists or doing some variations yourself.
Yeah. I think this was an amazing summary, Georg. It sounds easy, quote unquote, in practice, but what would you advise people to do? I asked the same question to Milovan Peric a couple of weeks ago, or months ago, and he kind of gave us like a guideline on how to start a simulation. So he basically said start very easy and then do all the adaptations step by step. Would you do the same thing?
This is exactly what we also do. Like if we have a complex task, we make it as easy as possible. And then we add complexity step by step, because if something goes wrong, then you know why it goes wrong. And if you put everything right up front and something goes wrong, you have no clue, then you have to go backwards. So I think it's always good to start to have the sparrow in the hand rather than the eagle on the roof. It's good to have something to start with, and then you build it up, rather than trying all complexity right from the start and then failing, and then you have to go backwards. It's easier to build things up step by step. So then I'm 100% in accord with Milovan.
Yeah, that makes sense. When it comes to some of the metrics for assessing simulation accuracy or quality, you mentioned some of those. Can you maybe summarize some of other quality metrics that you have a look at, and maybe that CFD practitioners can use on a day-to-day basis to assess the simulation?
Right. As I said, when we do projects, we usually quote the numerical, the iteration error and the discretization error. And if there are data, then we also compare the data. If not, which is for many industrial applications, you do the simulations because you don't have data, then you just have to tell them, using this and this model we have with this and this accuracy, these are the results. I think the other, so in the end, okay, this is a quality assurance after everything is done. But what we do also along the lines, like the first thing is we look at mesh quality in terms of mesh angles or skewness or whatever you name it, because they're all related. Then is expansion ratios, like how the mesh grows from small cells at the wall, for instance, to larger cells towards the inner volume. And also near wall distance of the first mesh point. These are typical things we look at, and we also make sure that if we refine the mesh by a factor 4 or 8, that these quality parameters don't change, so that the mesh is really scalable. And that's, I think, already a good start. If you have this, then I think you're with a reasonable code, you should get pretty good results.
Yeah, I think that makes sense. What do you think, Georg, do people get wrong? Because we talked about comparing to data. What do you think practitioners get wrong about verification and validation in CFD?
Okay, as I said, verification, what you can get wrong is that you don't do it. Like, as I said, I think you should for verifying a code, you should run on a sequence of meshes and then make sure that the errors decrease from mesh. If they don't, then either the first mesh was too coarse or there's something wrong with the code, some min-max statements which shouldn't be there, or some other thing. So that's verification. And validation, I think the main thing is that you have to have a very hard look what the experimentalists did, how they measured, how their uncertainty was, and how they defined the target quantities to compare with. I think that's the main thing. And if there are uncertain parameters like a turbulence intensity, you can, for instance, vary it from 5 to 8 or 7.5 or 10 and 2% and see if there's any influence. But I think that's what I would say includes, firstly, make sure that the numerics are okay, and then also have a hard look at the data. It's like my Wolfgang Rodi, my PhD supervisor, he asked me at that time you didn't have digital data, you measured the points from the publications. And then he asked me to do an integral of the velocity profiles to see if the same mass flow rate at every measure plane. And that's things we do sometimes now also. If we get, for instance, in the turbo machinery at certain places measurement data, then it's quite good to integrate them and see how much the mass flow rate varies, because the code conserves mass, and if the experiments don't quite conserve it because there's a certain variation, you can never meet them 100%. So I think looking at both sides is important for validation.
Absolutely.
And we talked about errors from beginners in CFD. And I have spent 6 years at a university institute in Erlangen whose main focus was laser Doppler anemometry at Professor Durst. And I can tell you that beginners in LDA make the same bloody mistakes that the other side also does. So I think on both sides you have to look very carefully.
Absolutely, that makes a lot of sense, Georg. There are some people who make the statement of that simulation kind of substitute experiments, but you would probably say the opposite, that kind of experiments and simulation go hand in hand. So one supports the other, so to speak.
I think they go hand in hand, but if you have validated enough, then I think you can say it partly replaces or at least reduces the amount of experiments. I know from our hydropower customers, if there's a refurbishment of a water turbine, like taking out an old 30-year-old runner and putting in a new one, the new design is only by CFD, because they know they get, without any expensive experiments, they get so much better with the CFD designs, then they don't need to do the experiments.
Yeah,
but then we also at ANSYS, we had customer from a large bus and truck manufacturer in Munich, and they said if you go in a bus and you said the steering system of this bus has been solely designed by simulation, you would be a little anxious. So I think it depends on the application.
Absolutely. Now that we talk about anecdotes, Georg, can you maybe give us some of the most, or maybe the most complex project you have worked on in the past? Can you think of some of the projects that have been super complex, you didn't know what to do, and then at the end of the day, it was kind of easy to figure out what the problem was from a CFD perspective?
I think when it was difficult at the beginning, it was also difficult at the end. I think it was mainly very, very complex geometries, like underhood of cars, or the internal cooling system of gas turbine blades, things like this. And then I think it's simply hard work to get a good mesh, so that you can do the simulation. So that can take a lot of time and can be frustrating. But if you have a good mesh in the end, the code converges well and the results are consistent, I think then you could say it makes life easier. And then I think the other things are when you have very complex physics, like with multiphase flow or combustion or chemical reactions, where not my strength, where you have to learn first what's going on in the first place. And that also can cause some frustration.
Yeah. When it comes to having a structured workflow in CFD, especially like whenever you approach a project, we talked about this, Milovan said the same thing, kind of starting simple and getting more and more complex. What would you maybe walk us step by step through? What would you advise people to do in terms of a workflow? How to set maybe define target quantities, for example, and then what would be the next step?
Yeah, I think we have this ISimQ workflow, which we also communicate in our short courses. It starts with setting the requirements, because I think that's very important, and the target quantities, because I think you have to really define what you want to simulate, especially when you work afterwards with computerized optimization. Then it's even more important to know what the target quantities are and what the constraints are. And then when we have defined the problem, we usually look at some non-dimensional numbers like Reynolds number, Mach number, Struhel, Root number, to see, okay, in which physics we have. And then we think about the model we would like to use, because model selection should become before geometry and mesh, because the model or the geometry and the mesh depend upon the model you use. Then, okay, depending if the Reynolds number is high or low, or Mach number high or low, we pre-select the models. Then we build a geometry model, do our mesh or our meshes, which, as I said, we always try for scalability. And we have our internal quality control parameters for mesh angles and expansion ratios. And I think what you see often wrong is that if you have prism layers close to a wall and then polyhedra on top of it, that there are large jumps between the two, that we try to avoid. Boundary initial conditions, solver parameters, and then the solution and post-processing, and then the quality control step. As I showed you, like iteration is part of the solution, but when you have 3 solutions, then or 2, you can quantify the results. And what I would also advise, I think, is to document along as you go. Because if you have written something, first of all, you can show it to a colleague. And I think writing something, you have to think about what you're doing more than if you just do it or hack it into the computer. And I think in software development, there is this concept that once you do something and then you have a code walkthrough with your colleague, I think you should also have a simulation walkthrough for complex problems that you document it in some form, and then if it's a complex new task, and then you discuss it with a colleague or other colleagues to make sure that you have done the right thing, and there's also buy-in from colleagues, managers, and so on.
Yeah.
Especially if it's not clear how to tackle the problem in the first place.
Yeah. When it comes to maybe managing CFD simulations and data in general, is there also kind of a best practice on how to deal with data, where to save it, how to capture it properly,
Yeah,
like knowledge management, as you said?
I think what I haven't mentioned about quality, I think, is discipline. I think first you yourself have to be disciplined, but even worse, when you work in a group, the group has to be disciplined, especially storing data. Things like storing data, which means everybody has to give a little so that the group wins, and giving a little or changing your practice a little for the benefit of the whole group is, I know it's a difficult management problem. So that's more on the human side, which is also an aspect. But I think the best thing would be to have some structured simulation data management where you can then, where you store some metadata up front and then the simulation data somewhere else so that you can quickly access them and then later also use for machine learning or other things. But I think I have not very often seen this done systematically in compasses, not even in ISimQ.
I see. Maybe let's take a step back and talk a little bit about CFD education. We talked about like what you do. You sometimes also have these congresses, right? Especially about turbo machinery, where you kind of meet and talk to all these experts and kind of do some seminars. Where do you see is the biggest problem right now, maybe in CFD education? We talked about not being practical enough. And where do you see the future of CFD education heading towards? Like, for example, students should maybe participate in some of the ISimQ classes or take specific books or courses. What would you recommend them to do?
Yeah, I think the best thing would be if the courses at the universities would be made more practical, and I think, for instance, I don't know any, not much lectures on mesh generation, for instance. And that's one of the most important parts in CFD. But I think in the courses, you mainly learn about differencing schemes and so on. And university, you hardly use the software in a structured, or people explain the how things work. But for instance, as I said, making it more practical, I think I would also teach more. There's also a theory about mesh generation and how you do it and what influences accuracy. That I think should be more, but I think in general more practical and turned towards more practice, and also more on the quality aspect, not just the theory of the methods, but also, okay, how theory and practice relate to each other, so that it's less of a, how do you say, black box or black science or mystery. But after all, I think CFD is deterministic, and it should come over like this.
Absolutely. Yeah, when I think back, especially back at the times at KIT, sometimes you have like these step-by-step instructions. Now click this button, then you click this button, whether that's FEM or CFD simulations. And I think sometimes you don't even know what you're clicking, what's
Right.
happening
I
behind
think
the
that's
scenes.
you have to get the background why, and if you do this, how the code should react, because there's a theory behind it, and also behind turbulence models. If you increase production, then you should have more of the quantity, and also understanding of conservation equations. Like I always in our courses, was it's like a bank account. If you have transfers, flow transport, which is like a transfer into the account. If you transport more in than out, the variable value goes up. You have source terms, which are like saving interest. Then nothing flows, but your account increases any K. You have debt interest, and you have two-phase flow, two bank accounts where you can shift your money around, but it doesn't get more. So I think it's also some, besides pure theory and mathematics, also a little bit of explanation what's behind it, and that everything is deterministic.
Absolutely. The courses that you offer at ISimQ, is it also for students? But because I think a lot of people who listen to the podcast, they would be interested in knowing if they could take some courses from you, for example. So is it only for professionals or also for students?
Yeah, right now we do the courses mainly for paying people, but uh, for people from industry and university, but they have a fee. But students could attend, but then they have to. We work together with a software company in the courses, and then you would have to register and see. Maybe you can get a bargain if you're a student.
So, yeah, we'll put all the links, the relevant links, down in the description of the podcast, and people can check it out. Obviously, Georg, before we head towards the end of the podcast and wrap it up, AI and CFD. What is your opinion on that? Where do you see the future heading towards? And do you think it actually makes sense to use AI for CFD? And when does it not make sense?
Different aspects. I think okay, what uh, what what we have seen, for instance, in model development. I think some of the turbulence model development, the trends of AI. It seems that you refine turbulence models based on numbers without a lot of physical insight and tune it to certain flows. I'm not very happy about this, because then, okay, if you need data first or if it only works for one kind of flow, then what do you do for the other kind of flow? So I think if it's used for model development, it has to be coupled with some kind of physical insight or some constraints, so that it's not purely numbers. Um, I think in optimization, or even in setting up simulations, I think you could put some of the best practices into some kind of AI application, so that you get good tips and hints from the software. And then in particular, I think if you combine it with a good simulation data management tool, I think you could use it to exploit the data and and arrive at better designs without doing too many simulations. But I think this is a bigger organizational task to have the data ready. Like, I think Google and these companies are the master. They can take unstructured data, unstructured in a general sense, and put it into structured information. And I think the same thing you would have to do with your simulation data, which different people store in different ways. But then to get key information out, if that would happen, I think that could really help the community.
Absolutely. Yeah, I 100% agree with you. I think it starts with data, and some companies that just want to use AI for AI's sake. So just jump on the
That's
hype train and use
a
AI just
hype,
to use.
yeah, right,
Exactly.
right, yeah.
Absolutely. Maybe to wrap it up, Georg, who should reach out to you? How can we reach out to ISimQ? And maybe closing remarks from your end to the CFD community out there. Maybe some motivating words from Georg.
I think on our website we have our telephone numbers and addresses. So from mail to phone to email is okay. There's also info@isimq.com.
Yep.
So whoever wants to reach out can reach out to us, and if we can help in some form or send information, then I think that's okay for us. So that's perfectly well, and we have started out to be a friendly company, which helps people and which provides with good solutions independent of the software, and so that's what we want to maintain.
Great. And then last but not least, some motivating words from Georg to the CFD community, and then we can wrap it up. Georg.
Motivating words. It's fun
Yeah.
to do CFD, especially if everything works. And
And
if
if it
you
doesn't
get
work,
consistent results. If it doesn't work, then you have to work harder. It's you have to work as long until you get satisfactory results. And I think that's sometimes a challenge, but in the end, it's fun. Like with everything in sports, in CFD, if you master something, at the end, it's fun. And I think
absolutely.
it's always challenging. I think CFD very often you are at where the research is, and that I think makes it even more rewarding.
Absolutely. Maybe the really last question right now. I think people will 100% ask this under the video. What resources do you recommend, like in terms of books, for example, or video courses? Let's say books. Which are your top 3 books on CFD?
Top 3 books in CFD.
Maybe one from Milovan. The one from Milovan is maybe on your
The
list.
one from Milovan, right? That's one. Then I think a good book, because I did my PhD in boundary layer. There's this viscous fluid flow by White, which I really liked. Turbulence modeling, there's a recent one, or not so recent one, a few years old, by Mike Leshziner about statistical turbulence models demystified, which is quite good. And then, because very often we have to do with compressible flow and thermodynamics. I like this engineering thermodynamics from Perkins and Reynolds a lot. I think these are some of the better books. But
Excellent.
I have a small list which I could also send out to people who are interested with.
That would be really cool. Yeah, then we can put it under the video and people can check it out. That would be really, really cool. All right, Georg, there was like almost a 40-minute podcast, a lot of insights, a lot of learnings for the CFD community out there. Thank you so much. And if people want to reach out, I will leave every relevant link down in the description. And then, reach out to Georg on
Okay,
LinkedIn or via info@isimq.de, I think. Yeah. Sorry.
ISimQ.com. Yeah, we are an international company.
Perfect. Cool. Then thank you so much, Georg. And hopefully we'll see each other in a second part in the future.
Okay, good. Thank you.
Cool.
Okay, see you.